Assalamu alaikum students. Welcome to lecture number 2 for our online classes. In this lecture we will discuss about the Ising model in the one dimension and the two dimension. So it will be interesting for you to understand the basic of magnetism, and the reference book is I already gave you in the soft form, the magnetism and condensed matter, and also you can find some supplementary material. So the Ising model, named after the physicist Ernst Ising, is a mathematical model of ferromagnetism and statistical mechanics. Initially, it was the first one-dimensional model which was solved by Ising in 1925, and there was no phase transition was seen in 1D, and he also concluded incorrectly that there will be no phase transition in the higher dimensions. The model consists of discrete variables that represent magnetic dipole moments of atomic spins, which can have two values, plus or minus, up and down. In the one dimension, the spins are arranged in a graph, usually like a lattice, where the local structure repeats periodically in odd direction like in solids, and allowing each spin to interact with its neighbor. So neighbor spins that agree have a lower energy than those that disagree. The system tends to stay in the lowest energy, but the heat disturbs this tendency, thus creating the possibility of different structural phases. The model also allows the identification of phase transition as a simplified model of reality. However, after this 1D model, the two-dimensional scale lattice Ising model was solved by some other scientist Onsager in 1944. He solved the 2D Ising model and also predicted the phase transition known as the TC, the critical temperature. Here is the example of one-dimensional Ising model. You can see the spins can be up or down. For up it's 1, for down its value is -1, and they can interact with neighbor spins. So the Ising model was invented by physicist Wilhelm Lenz in 1920, who gave it as a problem to his PhD student Ernst Ising. The 1D Ising model was solved by Ising in 1925 himself in his thesis in 1924, and it contains no phase transition, as we already discussed. And the two-dimension model scale lattice was much harder to solve and was solved by Lars Onsager in 1944. It is usually solved by transfer matrix method, although there exist different approaches more related to quantum field theory. So in the 1D model, the basics of the 1D model was the Hamiltonian. Consider a lattice with L2 sides and the connectivity of the scale lattice. Each lattice side has a single spin variable ±1, and if we have applied field, magnetic field is equal to small h, the Hamiltonian will be given as the first one is the Heisenberg energy or exchange energy, and the second one is the Zeeman energy, which tell us about the interaction of the magnetic field h, small h, with the spins. And the notation ij indicates that site I and j are nearest neighbors. The magnetic moment is given by S. In this equation, the j is the coupling exchange integral, as we discussed in the last lecture. If j is greater than 0, the system will be ferromagnetic. If the j is less than 0, the system will be antiferromagnetic. And if for paramagnetic system j is 0, we have no exchange interactions. The configuration probability is given by the Boltzmann distribution with the inverse temperature. Beta is greater than or equal to 0, and the probability of finding the system in state S can be written as exponential of minus beta h as a function of S divided by z beta in the subscript, and the z beta is subscript, as we discussed. This is the normalization constant, and it is called partition function in the statistical mechanics, and the inverse temperature is equal to 1 over kBT. So this P gives the probability of finding the system in state spin S. For a function f of the spins, the observable one denotes by function this f and beta in the subscript. This is the expectation value of the f. We have put the summation here because of discrete values of S. The configuration probabilities represents the probability that the system in a state with configuration S multiplied with the function f. Peierls extension shortly after the lens and Ising construction of the Ising model, Peierls was able to explicitly show that a phase transition can occur in 2 dimensions. To do this, he compared the high temperature and low temperature limits. He divides his model into 2 limits. And infinite temperature, when you have 1 over kBT, T is much higher, 1 over kBT will be tends to 0. All configuration have equal probability, which means we are in a state where every state has equal probability, or something like that. We are in a paramagnetic state. Each spin is completely independent of any other. There is no exchange interaction due to so much higher temperature, and if typical configuration at infinite temperature are plotted so that plus minus are represented with black and white, they look like television snow usually you see. For high but not infinite temperature, there are small correlation between the neighbor position. For low temperature, the snow tends to clump a little bit, but screen stays randomly looking, and there is no net excess of black and white. A quantitative measure of the excess is the magnetization. At low temperature, you have some alignment, and this magnetization is equal to 1 over n summation over S. At low temperatures, when the beta is much greater than 1, means that 1 over kBT, T is less than is very low, then the configuration are near the lowest energy configuration, and the one all the spins are plus or all the minus. The Peierls asked whether it is statistically possible at low temperature, starting with all the spin minus, to fluctuate a state where most of the spins are plus. To this happen, droplet of plus spin must be able to conjugate to make the plus state. Means he gave a concept of his transition in the ferromagnetic system, and this we know now it happens at a critical temperature Tc. And after that, Onsager in 1944 obtained the following analytical expression for the free energy of the Ising model in the 2-dimension scale lattice, when the magnetic field is 0 in the thermodynamic limit as a function of temperature. You can see the magnetization is changing at T is equal to Tc, which is the critical temperature. Below this temperature, the system in the ferromagnetic state, and above this, the system in the paramagnetic state. So he observed from his calculation that there is a phase transition in the 2D scale lattice. So from the Onsager theory, this is just an overview or quickly review of this theory. From Onsager's solution about Tc, 2 tan hyperbolic scale 2 beta j is equal to 1, and if you take it 2 beta j is equal to x and solve it, which is solved step by step in the slide, and you end up with the relation kBT is equal to 4j over natural log within the brackets 3 plus minus 2 under square root of 2. And if you put the values of this natural log and so on kBT, you end up with Tc is equal to 2.269 J over kB, which is the critical temperature for this scale lattice, and this phase transition is observed at Tc. So thank you, student, for understanding, and I hope it motivates you to read further from your textbooks and also from the literature and from the internet, and also from the related research articles. Thank you.